So let's take a look at an example of a scientific experiment with a short narrative and short data table, and break it down to identify the steps of the scientific method that are traditionally taught in grade school, high school, and college, where we have a question, a hypothesis, independent variable, dependent variable, things that are controlled or sometimes called constants to make the test a fair test, and ultimately the data that points to some sort of possible conclusion. So here's a very simple narrative prompt and an accompanying data table. A lot of standardized tests like ACTs will sometimes have formats that are quite similar to this. So here's our experiment. Jenny wanted to explore the relationship between temperature and chemical reactions. She tested aqueous solutions of food dye that are treated with drops of bleach at different temperatures. Let's say the aqueous solution was with a couple of drops of blue food dye. So the blue we assume is going to change color or change its intensity when it reacts with bleach. So she prepared 6 solutions by adding 2 drops of blue dye to 10 milliliters of deionized water and placed each in 50 milliliter test tubes. Each tube was placed in a warm water bath until reaching a specific temperature, then removed from the bath. 1 drop of bleach was added and the tube swirled 4 times as a stopwatch starts. So this would be an action that happened instantly as possible. We pull the test tube out of the water bath once the temperature's been reached, drop in the bleach, swirl, and immediately start the stopwatch. So probably have a helper doing it as the bleach was dropped in, or what have you. And then Jenny observed the number of seconds before the blue color began to fade. So as we can see, we have 6 different temperatures representing the 6 different test tubes of food dye solution that are treated with bleach, and we're looking to see if temperature has an effect on the amount of time it takes for the bleach to begin, quote, bleaching the color and making the color fade or change or whatever may happen. So we typically have, when we're asked to identify the steps of a scientific experiment, they'll give you maybe question, hypothesis, list 3 controls, 4 controls. They may say constants instead of controls. What's the independent variable of this experiment, the dependent variable, and a provisional conclusion. In some cases, there may be a set control group. Other experiments may not have one. This one really doesn't have one. So I made a point of making this word bolded out in red, relationship. Well, that gives us a dead giveaway of where we're going in this experiment. It's the relationship between temperature and chemical reactions. And we notice that temperature is essentially one of the data columns. That's a dead giveaway that is either the independent variable or the dependent variable. And then chemical reactions. So we're going to find out that the chemical reaction relationship is time, which is the other column. So generally when you have data tables, or they could be graphed as a line, it doesn't matter. Generally, your data in a simple single variable experiment will represent the independent and dependent variables. And those 2 elements of the experiment logically would be in your question in some form or another, and your hypothesis, which is a suggested possible answer to the question. Our conclusion essentially should also reference the independent and dependent variables. So the independent and dependent variables that are embedded in the text and in this data table should be referenced in some form or another in the question, the hypothesis, the independent variables, and the conclusion. So it's a very interrelated, interconnected way of looking at how an experiment is designed. So we have our relationship. So we have temperature. There's a dead giveaway that we're looking to see if we are manipulating the test tubes by temperature. Well, that's the independent variable. That's what we're assuming is going to cause some sort of difference in the time that it takes for the chemical reaction to begin. So we could ask this as a question if we're exploring the relationship between temperature and the speed of a reaction. Well, we could frame that in a question. We could say, well, what is the relationship between the temperature of a chemical reaction and the speed at which it occurs, or the rate at which it occurs? So we can put, and this isn't the only way that we can actually word this question, but let's just go ahead and do it this way. So what is So I'm kind of shorthanding this because I don't have a ton of space here. But what is the relationship between T, temperature, and the speed of a reaction? So this question is really open-ended. We don't know if it'll have an effect at all. We don't know if warmer temperatures will make this reaction speed up, or if warmer temperatures may make it slow down. Some chemical reactions go one way, and some go the other way. We don't know yet. I wouldn't get too hung up on like what we're going to predict or whatever. We kind of have the data already the way it's presented here, so we could just kind of go with what we already know the relationship seems to be, and we could just simply say, well, we hypothesize that the warmer the temperature, the faster the reaction. The RXN react. This is often the way teachers will, and chemistry teachers, they will shorten reaction into RXN, so go ahead and get used to that. You'll see me do that some when we're in a hurry. And so what are the controls? What are we doing to make sure that this data here is valid, that it was a fair test? Well, what I decided to do was simply underline in green the elements in the text that represent the way that all of these test tubes, these are our 6 trials, were kept the same for it to be fair. Well, obviously, what we did is we had 2 drops of blue dye. Well, that's each test tube got 2 drops of blue dye. That's a control. They were all in 10 milliliters of deionized water. We didn't have it where some were in tap water and some were in deionized. They were all in solutions, aqueous solutions of pure deionized water. And all of these were in an environment of a 50 milliliter test tube. There's 3 right there. If you wanted to be really smarty, you could just say, well, it was in 10 milliliters of water and all the water was deionized. You make it 4 or whatever if you're splitting and trying to fill up a quiz. They're all placed in a warm water bath until reaching a specific temperature. Now the temperature is not a control. The temperature is the independent variable. That's the difference between all of these test tubes. However, the reaction involved all of them getting 1 drop of bleach, okay? That's a control. So our chemical reaction was, our 2 reactants are, everything was the same 10 milliliters of water with 2 drops of food dye solution treated with 1 drop of bleach. So all of these tubes had the same actual chemical reaction, both quantitatively and qualitatively. They all got the same bleach. You know, they were all had the same concentration of food dye. The only difference is the temperatures at which the reactions began. That obviously is a difference, that is significance, and that is basically driving the reaction. So the independent variable here is the temperature. The temperature of what? Of the reaction itself. Always be specific. Temperature of what? The temperature of the reaction. The temperature, or you could say the temperature of the test tube itself, because that's the environment in which the reaction is happening. So that would be, you know, if I were a teacher, I'd of you in this particular exercise, okay, as long as they said the tube, that's fine. The temperature of the tube, or the temperature reaction, I would take either, that's fine. But don't just say temperature. Do try to be specific here. What's the dependent variable? Well, yes, I know it's time, but what is, I would say, time in seconds, because that's how we're measuring time here. That's the international standard for color to, we could say, you know, saying it begins to weaken, it begins to lighten, it begins to bleach out. We could just say color to shift. But we can't just simply say color, and we can't just simply say time. Your teacher wants to know, what do you mean by that? It was the time for the color change to begin. Okay? That is specific. That's what the data table is. Notice how in data tables and experiments, normally the headers of columns in a data table contain the independent and dependent variable. If I had done this as a line graph, they would be the x and y axis of a line table. It doesn't matter. And so our conclusion is, we do see, if we graphed this out, we would see it wouldn't be perfectly linear, but it's a clear trend to the idea is that the warmer the temperature of the reaction, of the Rx in reaction, the faster the reaction. At least that's what the data supports. This is a narrow range of temperatures. We could, in theory, move it to 60 and 70, 80, or maybe even 90 before the water just starts boiling at 100 degrees under normal conditions. But the data supports this trend. This just says that the data supports this. This isn't the gospel truth. The data just does seem to support this. Okay, so going back over this, generally when we have these narrative-based experiments that have a data table, you often look to the narrative itself to get your controls. And just to give you context, but generally you will find that in simple single variable experiments that we tend to encounter in high school and for early year colleges, is that we're going to have a single independent variable that will occupy one factor, one data factor, and then a dependent variable that responds to that. It depends on this. So when you're trying to remember independent versus dependent variable, do bear in mind that this depends on this. This comes first. We basically make the independent variable part of the design itself. Then the dependent variable is what we're watching to see happen here. So in conclusion, it's not hard to pick out where the elements of a scientific experiment are If you simply know that you need to decode a few basic things of how the test conditions are kept similar, that's your controls, or sometimes called the constants, and the relationship between the independent and dependent variable, both of which should be embedded some way or another in the question, in the hypothesis, and in the conclusion.